Recording in progress.
Hello, hello, hello. Hello. Hello, Charlotte. Good afternoon, Alexis. Hello, Penina. Hello. Good afternoon. Okay, wait, there's more people coming. Hang on. But yes, good to see you. Wait, is that feedback coming from me? Hang on, I'm
That
sorry.
was Penina. She submitted her shit.
Okay, sorry. Okay. Thank you. So hello, Christopher. Wait, all right, I'm still okay. Sorry, I'm just catching up with myself here. So hello, Charday. Good afternoon, Alexis. Hi, Penina. Good afternoon, Juliana. Good afternoon, Key. Good afternoon, Gretchen. Good afternoon, Michaela. Hello, Samantha. Awesome. Oh yeah, I guess. And good afternoon, James. Excellent. All right. Hello, everybody. Oh, more people. Okay. All right, we're gonna is that okay? Is this yeah. Okay. Okay. So it's the last week of class. There's a lot of stuff. I mean, there's still material, of course, to finish the most exciting material in a way. But there's also a lot, of course, I'm most concerned about the material at this point, but of course I understand that you all would be most concerned about your outcomes and your grades and all that. So I put a bunch of things in the Google Classroom, hopefully to save a little time today, because I know there's, of course, people always have questions and concerns, and at this stage of the semester, I want to spend as little time as I can of the class time today addressing all of that, but hopefully a lot of the stuff in Google Classroom will clarify. Here's the quick summary for right now. And let me say that, as always, it's always true, but especially this week, especially this week, whatever personal concerns you have or academic concern, whatever, hang out right after class is really the office hour time. It's the best time for me to answer questions. If they're private, I'll take them one by one. If they're about the material, I'll address everybody at the same time. But I don't leave. I will not leave this class at the end of a Zoom session until everybody else of all of you has left. Okay, so again, just to say, I'm always a bit more. We're always a little bit more relaxed after class than before. Okay, so please hang out after class if anything I'm about to say is unclear, or if anything in the Google Classroom is unclear. And good afternoon, Dante. Awesome, and good afternoon. Someone else just came. Well, good afternoon, other people who just came. So just to reiterate, number one, about half of you or a little bit more have gotten your exams back. Many of you still have not. It is largely random, except that it is true that if you happen to turn an exam late for whatever reason, even if we totally agree that you could and all that, then you're probably not getting your exam back first. But that's not a punishment. You're still going to get, all the points you deserve, all that. But it is true that anybody who somehow got it in time is getting theirs back first. Okay, so if you haven't gotten your exam back yet, I know that causes anxiety, and it's coming as fast. The machine is really cooking now, so you should be getting them very, very soon. And maybe some of the other information that I post in Google Classroom will give you a little bit more perspective on where you stand until you actually get your number. But I think it's fair to say the quick thing, and if you have gotten a number or you have issues about your exam or something, again, hang out right after class. But I will say again, of course, the exam scores are always, the midterm scores are always lower in a way than people would expect or people would want or whatever. And there's a lot of stuff built into this grading system so that your midterm score is not, you shouldn't read your midterm score as like the final letter grade that you're getting in this class. There's other things that get factored in. I don't want to dwell on this for too long. Obviously, this will be an easier speech to make when everybody has theirs back. But the main theme I'm seeing so far, okay, because I know now we have to get to the final exam. As I indicated in Google Classroom, your final exam will be a smaller, less intensive or demanding experience for you than your midterm was. And partly that's because I know it's taken a while for you to get your midterms back. I totally understand that. And it's a fast moving course. So your final exam is designed to be an opportunity to help your grade for those of you who end up finding out that you need that after your midterm, right? And as it indicated in Google Classroom, if you do better on your final, even though it will be a smaller experience, then that will help you more. But for those of you who got anywhere in the 80s or higher in the midterm, you should definitely feel like you're in solid shape. And the final exam, you should still study for the final exam. You still have to take it. It'll still count. But whatever you did on your midterm, if you're in the 80s and possibly even in the high 70s, but if you're like in the high 70s or the 80s and 90s, then the basic idea of what you did in your midterm is what you should try to do again in your final exam. And if you're lower than that, I'm not saying that you're failing the course or something like that. But if you're lower than that, there's probably something that you need to tweak for the final. And you have the opportunity to do that. And if you do better on the final, it'll count more for you, as indicated. And the main thing, very quickly again, to say to everybody, whether you've gotten a midterm back or not, the main thing that's really separating the sort of more the scores that you want from the scores that maybe you're disappointed by, the main thing that's separating them is really how user-friendly, how reader-friendly, how well and clearly presented is your document. Your goal in the document is to prove that you understand all these things by you doing all the work. You want to make the reader, i.e. me, do as little work as possible to follow everything you're doing. It's a presentation, so the more you can do to spread out your work, to make the order of the steps really clear. The order of the steps is in order for a reason. Follow the order of the steps, make it super clear, spread it out, make things big, et cetera, et cetera. And again, if you did get yours back and you're frustrated with your score, of course I can answer individual questions, not in the middle of the class. And maybe I made mistakes here and there. Of course, I'm open to that possibility. But focus on how hard you were working to present a final draft that caused me as little work as possible to follow. Okay. And again, if you got one back and your score is like in the 50s or 60s, that does not automatically mean you're failing the course or anything like that. I just want to say that again. It does mean there's something you need to do for the final. And if that means texting me, making a quick appointment or something, do so. Last thing, but for the most part, we're all here together. We're all still hanging in. We're all still looking for all of us to do as well as possible. It's still not a competition. It is a cooperation, honestly. And, and if there's a particular concern with you in personal, either you're going to reach out to me or you will hear me reach out to you. Okay. But the game is not over or something unless we actually have a conversation to that effect. Okay. I want to move on. But also, like it says in Google Classroom, materials for the final exam will be posted in time for you to, just like last time, you're going to have like a practice experience on the last day, Wednesday, with in lab with Professor Talley. So everything is rushed in this course because it's 5 weeks, but you'll get a document in time to practice on Wednesday. Then the actual thing will be posted Wednesday night, even though technically all this is supposed to end Wednesday night or maybe Thursday. Technically, I'm trying to correspond with what Professor Talley also came to understand, which is that technically our grades are not due till Monday. On the other hand, they really are due Monday. So that's a little extra time for me, but it is a rigid time. So the bottom line is, yes, we're saying your final exam, you'll practice it Wednesday with Professor Talley. It will be short. You'll have a lot of choices on it. But then it'll be posted Wednesday night. You'll turn it in by Friday night. I mean, that's a fast turnaround, but you'll turn it in Friday night so I can grade everything and get your grades to the registrar by Monday. And the registrar has no flexibility on that. I've learned the hard way over decades. And I can't submit any grades until I submit all grades. So that's the deal. Again, I'm trying to be a little bit fast now, just so you know the story. And you can ask me personal questions. Okay, I'm going to look in the chat, but I'm still available by text and by email. But we're in a fast last stage till the end now. Okay. Good afternoon, everybody. Okay, good afternoon. Thank you. Okay, I know not everything may be perfectly. Let me just say this. Can you just raise your electronic hand if you saw that much of this information was just posted in Google Classroom, so you can sort of. Okay, great. Okay. So you can, great, thank you. So you can reconsult that for nuances and all of that, and great. And a lot of the exams are really good. Okay, I mean, and the ones that if you had, I'm just gonna say again, if you got one back and you got a score that was like in the 50s or the 60s, I'm sure you found that sort of alarming. And it does mean there's something that needs to be done, but it doesn't mean that the game is over for you. That's like the simplest thing I can say. Okay. All right. So now we're going to get back to material. And any material we're doing now, I'm only doing material that you need for the final exam. I assure you of that. And the final exam is only on, directly speaking, any of this material that we've been doing since the midterm. Okay. All this field stuff, really. So, okay. Sorry, I'm going to take it. And if I sound, I don't mean to stress anybody. I always sound this way at the end too, just because I'm also concerned about time. But the goal is for everybody to do well still. And also the goal is to like understand and like some physics by the end. So, all right, so here we go. Yeah, the goal today is to get back to electrostatic fields, to get back to this concept of electrostatic fields, which ultimately link back to the circuit stuff you've been doing in the lab. It's all related anyway. Okay. The goal is to get back to electrostatic fields. We did that long problem last time that shows you how to compute the electrostatic field at a point in space due to 2 points of electrostatic charge, right? Now where we want to go to today is we want to back up and give more techniques and representations for dealing with more than 2 points of charge, for dealing with like reality, something closer to reality. So it's not just that we want to now deal with like 3 points of charge or 4 points of charge or 5. What we really want to start dealing with now, I'll write this right here on the page, one of the last like topics of everything we do here is what we're really interested in now. How can I write this? I knew I wasn't going to do this. Okay. The main focus of today and tomorrow is source charge distributions that are continuous, right? Not even just like a whole bunch of points, but a whole of charge, but a whole bunch of points of charge that are so close together that the space between them could be said to be infinitely divisible. We want to now look at a whole, instead of a bunch, we want to look at charge collections that are less similar to a bunch of grains of sand and more similar to like a stream of water, if you know what I'm saying. That's an analogy. But I'm saying we don't want to look at quantized, discrete, countable points anymore. We want to look at what would be more our macroscopic experience in reality. We want to look at smears of charge, like a line of charge or a plate of charge or a sphere of charge, shapes, right? Which is more what we encounter in macroscopic reality. So we have techniques for dealing with that. The ultimate premise of these techniques is that we do believe that the whole is equal to the sum of its parts. We do believe that if the field over here at some point in space is the sum of the field due to a point over there plus a point over there, we believe that if we had a whole bunch of points infinitely close together, continuously collected so as to make some big shape, we do believe that the field due to that shape should be the sum of the field contributions produced by all of the points in the shape. But I'm going to say, and then I'm going to look in the chat, but I'm going to say now so we still believe the whole is equal to the sum of its parts, We believe that forces and fields obey superposition, as we always have believed in the case of, for example, Newton's second law, sum of the forces equals mass times acceleration. So, but we also believe that we have this technique in calculus called an integral, which allows us to perform a continuous sum, right? A sum over pieces that are infinitely small and infinitely close to one another. So we're going to start introducing some pictures, some visualizing techniques and calculus techniques for computing the field over here in some point in space due to a continuous collection or continuous distribution of charge over there at that point in space. I'm going to say that sentence one more time. I encourage you to write it down. Then I'm going to look in the chat, then I'm going to turn the page. But the real goal of classical electrostatic study, the goal of the classical study of electrostatics is this. It's this. Given some continuous collection of source charge over here, can we determine a function to describe the electrostatic field over there? Given a smear of charge over here, what is the field over there? That's our ultimate goal of electrostatics. If the collections of charge are continuous, then we need sort of advanced picture or representation techniques and advanced calculus in order to answer that question. Last time, the question is, given a continuous collection of charge at some location in space, what is the electrostatic field at some other location in space, separated by a displacement r? Okay, so I'm going to look in the, I see there's at least one thing in the chat. Maybe it's probably, I don't know. And then I'm going to turn the page and go on. Hold on. Okay, private question in the chat. I'm going to answer private. Hold on one second. Okay. Well, actually, one more thing. So, okay. Okay. Some good questions in the chat. A couple of good questions in the private chat. I just responded privately, or directly. Okay. So, all right. So the first thing we're going to do right now is I'm going to introduce a new representation technique, a new visualizing model tool for fields. I'm not making it up. It's like very standard. You'll see what I mean. But okay. Okay. So one thing I'm just saying here on the board, I'll just read my handwriting. Let's introduce a new technique for visually representing fields in space. We need a new technique if we are going to confront, that says confront, okay. We need a new technique if we are going to confront continuous charge distributions. Okay, now I'm building this up a little bit more than necessary, but this is, so we're going to make a new visual representation here, and it's not just a sketch, it's a tool. Just like graphs are literally a computational tool as well as a representational tool, and just like vectors are not just, don't just give us a rough way of visualizing things, but in fact vectors are a tool for computation. We're going to introduce a new and crucial and classic tool for visually representing fields and ultimately doing computations for fields. Okay, and you're going to recognize this when you see it. The new technique. Let's build and explain electrostatic field lines. Okay, this is the topic for right now. Okay, what we're going to explain now is how field lines work. Let me again, it's something you've sort of seen a million pictures of on the internet and stuff like that. I mean, I think you've been exposed to these in some way your whole life, but they're a very specific thing. And if you're anything like me, you may have seen them or heard of them, but you don't necessarily exactly, well, I didn't ever know exactly what they were showing or what they meant. Oh, is that a hand up? I never know how to, if that's a hand up, let me know. Wait, sorry. If there's a hand, put it in the chat. Okay. Oh, someone is here. Okay. So I want to explain exactly how field lines work. Again, they're like graphs or vectors. They're a real thing. They're not just like a rough sketch notion. We're going to construct them or develop them from a tool we already have, from vector. We'll develop field line, diagrams from vector field diagrams. So I have to be this. Someone was actually asking like an analogy in the chat. Here's one analogy, and analogies are always a little bit dangerous, but like much like with simple harmonic oscillation and waves, they're not the same thing, right? And I think a lot of you really ultimately got that across in your exams, but we needed simple harmonic oscillation in order to build waves from them. Okay, similarly here, I'm going to refer us back right now to a couple of crucial vector field diagrams. That's what we were all dealing with the last 2 days of last week. I'm going to refer your attention back to vector field diagrams, but it is so that from them, I can construct this new idea called field line diagrams. They are different, okay? The old news is vector field diagrams. From them, we're going to construct the new news here, which is field line diagrams. I'm going to show you, but please keep them straight in your mind. They sound similar, they look similar, but they are different. Okay, so I'm going to say, recall. This right here, oops, sorry. Okay, what I'm drawing right now, right? This is the vector. This is old news right now, a stepping stone. This is the vector field diagram of a positive point source known as plus Q. Okay, so this right here, old news again, this is a diagram, a representation of what the electrostatic field produced by a positive point source looks like, right? And this was our original notion of field. Like if you put like a proton, right, in the middle of the lab or on a table in the lab or in the middle of somewhere in outer space, you just put an isolated proton, a point of positive electrical charge somewhere. What we believe, right, is that everywhere in space surrounding that positive point, there are forces, electrostatic forces waiting to happen, right? This is the whole idea of a field. Every one of these arrows is representative. Like what we believe is that if you think of an arrow, a field vector, as representing a force per charge, magnitude and direction at the tail of the arrow, right? Again, this is a reminder of what in theory we know from last time. Like if I just pick this random point right here, point P, right? The fact that there's like a little arrow pointing up from that, with its tail at that red dot is supposed to be telling me, okay, if I were a 1 coulomb of positive test charge, if I were a test charge of positive 1 coulomb located at that red point, I would be pushed up, like I'd be pushed away from the positive capital Q source charge, right? I'd be pushed away with some number of newtons. The number of newtons I could infer from this diagram if I had like a scaling factor that I had agreed on in advance, right? Like I could tell from the diagram right away from that arrow that's pointing up that I'd be pushed up. Why? Because I'd be pushed away from the source, along the line that connects the source to me. I'd be pushed up, and I'd be pushed up with some amount that's less than what I'd be pushed up with if I were like down here closer to the source, or more than if I were up here above the red dot, right? So that arrow is showing me comparative magnitude and direction of force waiting to happen. And all the arrows are showing that. And they're all showing it comparatively, like qualitatively. But if I drew this to scale and I had a scaling factor in mind, they would literally be showing me quantitatively the kind of newtons per coulomb that's waiting to act at every single one of those points in space. And again, to remind you, this is just a representation, right? In theory, if we understand this, they're not in theory. In reality, there's arrows everywhere. Now, again, it's a funny thing to say because I don't really believe there's arrows in space. I mean, I don't believe there's solid objects that look like arrows in space. But what I do believe is that everywhere in space, there's a magnitude and a direction of newtons per coulomb waiting to act on any test charge that could ever find itself anywhere in space, right? And so we draw just enough arrows to show the pattern, right? There's nothing special about where I chose to draw arrows. I just picked a certain number of arrows in certain, arrangement of them just to ultimately get across the pattern of the arrows. And the key point of this pattern is if it's the vector field diagram produced by a positive point source, then what you see is a bunch of arrows that radiate out from the source, as opposed to if the source were negative, they radiate in, right? And they get smaller and smaller as we get farther and farther away, right? That's the pattern. Okay, that's a vector field. I'm just going to say again, if I were doing the vector field diagram of a negative source or due to a negative source, then it would be the exact same picture, but all the arrows would be pointing in, right? Okay, so that's that's from last week. Now, that is a diagram representation that puts an arrow at every point in space. It's a fairly simple way to picture how the information is arranged in real space. But here's the thing. It's pretty simple, hopefully, not easy, but simple, just like arrows, right? But even for something pretty simple, it's still pretty complicated because this is just the field being produced by a dot. Again, what you were sort of meant to take away from that complicated problem that we went over last Wednesday, which will be one of the choices on the final exam, you were supposed to take away that dots are so complicated. The minute there's even 2 dots, things get really hairy really fast, right? This is a lot of arrows to draw just to get across the idea of what 1 dot is doing to space. So the question arises, might there be a slightly simpler way to convey all of this? And there is. What I'm going to do now, and bear with me, please, or stay with me. This is a vector field diagram. It's by the way, it's completely correct. You could type into Google like vector field diagram from a pointer, and you'll get it. Like it's valid. There's nothing wrong with it, but it's a little old-fashioned because it's like a lot to draw, even in the simplest possible case. And please understand, if I had 2 dots or 3 dots or a line of charge, oh my God, there'd be like the arrow arrangement gets really hard to draw really fast. So we develop instead, or Michael Faraday, great physicist who was really a chemist, who was really a high school chemistry teacher of the late 18th century, early 19th century, Michael Faraday developed this idea called field lines, which are built from these vectors, but are actually a simpler, more smooth, continuous way to think about this stuff. So what I'm going to do on the next page is say, let's instead propose. I mean, we're not really proposing it. Like this is reality now, but let's propose a field line diagram due to positive point source plus Q. Okay, and it will, okay, now this is not going to be, it's not going to look like a radical change to you just yet because we're still doing 1 point, but it is a change. Here is now, instead, that was the vector field diagram where we draw a bunch of vectors to depict the field. Now, instead, we're going to draw a bunch of field lines to depict the field. I'm going to change color. It will look like this. Now, and again, this is the field line picture due to a positive point source. The field line picture due to a positive looks like this. And I'm just changing the colors so you can see the distinction, but there's no rule about the colors or anything. Okay, now that's the field line picture. Let me explain what I just did. Now you might say, really? Like all of your talking, it's not that different. Yeah, it's not that different. It's just different enough to make our life a lot better once things get slightly more complicated. Here's the difference in what I just drew. And I'm going to break it down. Basically, what I did was I sewed up all the arrows. Like, whereas here you have arrows. Yeah. Hold on. So, good question in the chat. Hang on. Was that? Okay. All right. So the chat says, can I please repeat what I said when I started drawing the field? I was cutting out a little bit. Okay. Unfortunately, I'm not sure I remember exactly what I was. When I was drawing this, okay, I don't remember exactly. Here's what I should say. I'm saying that what I did to go from this to this, what I did was just connect up all the arrows. That's all I did, but that's a big, big deal. All I did was connect all the arrows. Where in this picture, I have a series, like right here, for example, I have a sequence of increasingly shorter and shorter arrows going off on a radial line. In this new, and those are each vectors, right? Like at each point, I'm drawing a representative vector. And please understand again, like the idea behind this original drawing is I'm just picking representative spots. Like I could have broken it down further and had even more arrows. But the whole idea is that at every point, I draw an arrow whose orientation is the direction of the field and whose length is the magnitude of the field, right? That's the idea, but of the vector field picture. But in the field line diagram, I get rid of all the arrows. I don't have a bunch of tails and tips anymore. All the arrows that were pointing along a given radial line are all connected into one now. This is the big difference. It is a big difference. So I'll write that. So these are no longer vectors. You're going to see what I mean. These are not vectors anymore. They are arrows, but they're not vectors. They're called field lines now. They work their representation is very different. Remember again that with a vector arrow, the whole idea is its tip-tail orientation represents direction and its length represents magnitude. Here, these are arrows. Yes, they are arrows, but they are not vectors. And the main reason they're not vectors is as I'm going to explain to you more, it is no longer the case with these arrows that length of arrow represents magnitude. We're getting rid of that idea. We don't have shorter arrows and longer arrows anymore. I just connected up all the arrows into one big one. Okay. The goal, so let me first just write that down. So I'm saying we've connected a lot of the arrows that were before. The goal of connecting them is to make our diagram simpler so that we could still handle much more complicated arrangements. Okay. It doesn't look that much simpler because we're still just dealing with one point, but it is simpler. Let me start breaking this down further. Okay. Okay. I'm going to, and by the way, a direct chat person who asked me to repeat what I said, just let me know maybe in the direct chat whether, I don't think I repeated exactly what I said because I don't think I remember exactly what I said, but just let me know if it sounds like I got across whatever it was that you needed me to get across. Okay. So these are field lines now. I got to tell you in detail now the difference between field lines and vectors. Oh, okay, great. Okay, cool. Thank you for the thank you. Okay. So I'm going to give you now. Oh, and I'll also, just to be clear too, just to complete this page, if I had the field line diagram from a negative point source, as you might expect, it would look like this. I mean, same thing as before, only, pointing in rather than pointing out. Again, just like before, the whole idea of these lines, like their representation, I believe fields are real. Fields exist in space. Anytime anything exists in space, it creates a field in space. What's really actually in space is information everywhere in space, right? Whether we're going to depict the information in our brains and on our paper as little arrows or long arrows, whether we call them field vectors or field lines, it's all just a way of representing it in our mind. It's just like graphs. Like, we don't really think graphs are like literally in space and time, right? But we think that graphs are a way of representing information in our mind that's actually happening in space and time. So you have to, so this is like serious. It's just like learning about graphs or vectors when you're younger. We're learning about information and how it's organized in space. But you always have to keep in mind, like, what we're talking about here on the paper is our mental representation of what we actually believe is out there. Okay. So I'm going to write in a minute. I'm going to give you a set of rules for drawing and reading, for creating and interpreting field line diagrams. That's my goal of the first half of today's class, is I want to give you the rules for what these field lines actually mean. I mean, that's what I'm about to do. I'm just thinking, give me 1 second. All right, yeah, I'm going to start doing that right now. But then I'm going to show you a bunch of different diagrams, like on Google Images, so we can get perspective on this. So here we go. Actually, no, I'm going to go right now. I'm going to, wait, there's something in the chat. Okay. I'm going to say, our goal Wait, okay. I see something in the chat. Hang on a second. Oh, okay. My goal here, is to not take all class periods, but to take a few minutes to lay out exactly what these field lines, what they mean, what they're representing, and how. Much in the same way that with vectors, you have these rules like the tip tail orientation is the direction and the length is the magnitude. We have similar rules for these, but they're a little bit more elaborate, and that's what I want to give you. But I think they'll be easiest for you to see the rules if I switch screens in a moment and show you some examples of what field lines look like. Let me check. Oh. Hold on one second. There's just something in the chat I can answer. Oh, I can answer privately. Just give me a second. Hold on. Oh, yeah. Okay. Okay. So I'm going to go back and forth between screens. The thing I'm going to do now, give me a second. I want to show you. I found in the past that the easiest thing to do is, give me a second. Right. Right. Okay. Ooh. Well, okay. I'm actually, here we go. I'm just going to, this is like ridiculous, but what I'm about to do is obviously something you can do at any time at home. You could do it right now. If I were to physical, you could just do it, but I just want to get on the same page with you. If you, I believe I've just, yeah. So all I did, you can see, all I did was type in E field line diagrams. I think that's what I typed in. I typed in E field line diagrams into Google Images, right? And all this stuff comes up, as you can see, right? And some of this I want to go through thoroughly with you, but right now, first, I just want to give you perspective, like, if I can, like, oh, for heaven's sake, come on. And obviously this is all like copyrighted material. Hopefully all the proper citations are right here in the images. You could type in the links yourself. I'm not claiming any credit for any of this. I don't mean to be. Okay, yeah, I just want you to see like what I'm scrolling through somewhat quickly right now on the screen. These are various different field line diagrams for different possible charge arrangements. Okay, now even so, this one right here is the field line, the one in the center of your screen is the field line diagram representing the field in space due to two nearby positive point charges. Okay, that's just two charges. Again, this is a field line diagram now. That this already maybe looks a little bit elaborate. Maybe it looks beautiful to you. Maybe it looks intimidating to you. But the one thing I want you to notice right now when you're looking at it, the first thing I want you to notice is that this is all field lines. Like there isn't a vector drawn at every single point in space. All the vectors have been sewn together, right? So this diagram, as elaborate as it might look to you, would be even more elaborate if it was all a bunch of vectors, right? So the first idea of field line diagrams is it's meant to make our life simpler. It's actually meant to convey a ton of information in a manner that would be very, very, very difficult if we had to draw a separate arrow at every representative point, okay? And again, just like with the arrows, even these field lines that you're seeing here, they're just at representative regions. Like in theory, this represents a slice of space for which there's actually some kind of line everywhere in space, but this is the pattern, right? Now I'm going to keep scrolling for a second. So you can see what's below it. We, in the center of the screen right now, we have the field line diagram from two nearby negative point charges, i.e. like an electron near another electron, then over to the, as it says right in the screen. Next to that, we have the field line diagram of a dipole, of two charges nearby, two point charges that are opposite in charge but equal in magnitude. Right now, look at that for a minute. I mean, that's fairly elaborate already. Remember, right? And it's maybe unexpected until you understand how to read this picture or write it, which is what I want to tell you next. There's obviously some kind of, or I shouldn't say obvious, there's a pattern there. There's something organized about it, but, I don't know that you can immediately tell what the pattern is trying to say, or I don't know that we could immediately have come up with that pattern unless I tell you some rules for this in a minute. But I'm going to keep scrolling for a second just to see. Now you see things are getting even more elaborate. If you go all the way down, I mean, you can look for yourself and you can poke around yourself. If you look at the bottom two pictures of these four that are in the center of your screen, and I believe you could tell me if you can't see them. I think you can. For heaven's sakes. Okay. If you look at the bottom two there's something very patterned about those pictures, but each pattern is now a different pattern, and they're sort of getting more and more elaborate, right? What's getting more complicated about these line diagrams is that the very source that's creating them is getting increasingly complicated. Like in the bottom two pictures, well, as it says, you have opposite point charges near each other, but they're opposite direction, opposite sign, but they're of unequal magnitude. Right? So the pattern is there's always some kind of symmetry in each picture, but as the source distribution gets more and more asymmetric, then the field lines convey more and more asymmetry. And in fact, that's totally not a coincidence. That's the whole idea of them. I just want you to get a sense of how these things work. Now, even all these, as elaborate as they are just the field lines from various groups of points. We haven't even gotten to the actual goal yet, which I think we might in this website. The actual goal, maybe not in this website. Oh, wait, maybe. Well, no, these are all, okay. Wait, these are all, hold on. Oh, look how complicated that one goes at the bottom. But, I just want to, whether I find one quickly or not right now, just note that all those diagrams were still caused by point sources assembled in some way. Our ultimate goal is to look at, in fact, okay, I'll just type it in. Our ultimate goal is to look at fields and field lines. Sorry. So why is it? Okay. From continuous charge distribution. If this doesn't work immediately, I won't go down this rabbit hole for too long, but by which I mean what we ultimately want is to be able to look at the field from like a line or a plate or a sphere of charge. And if this loads, it loads, and if it doesn't, it doesn't. While it's loading, I hope you notice I hope I just showed you just enough of a quick sample of field line pictures for you to notice all these field lines, they are arrows. Oh, they most certainly do have tips, and tails sometimes. But I hope you saw that these arrows, they curve, right? I mean, a lot of those lines were curved. So this is and that's very important. And it's not and it's true. It's a very, okay, maybe it's not good. All right, if this doesn't load, it doesn't matter. Field lines can curve, which I'm going to get to in a minute. So, okay, it can't, all right, it's all right. We'll go back to Yeah, all right. Yeah, and you can obviously do this on your own too, but okay, main rules. All right, we're going to switch back to the other, and there's things in the chat. Oh, wait, before I'm going to switch back to my screen and start explaining this, but maybe these questions in the chat need to be answered. Oh, are you not hearing me? Wait, sorry. Oh, okay. You know what? I'm sorry. I'm seeing in the chat that there's like, if there's lagging, it's probably because I'm trying to load websites and stuff. So I'll stop that here. I apologize. Hang on. We don't need that anymore. That may be why. Hold on. Okay, wait. All right. Tell me if right now. Okay, sorry. Are we back better? If it was lagging, I see that there was lagging stuff. I apologize. Better. Okay. So I think that's because okay. So I apologize. Look, the summary of all that. Okay, cool. Thank you. And I really do appreciate how much you all pay attention. The summary, you could do that on your own. You could type in field line diagrams into Google Images, and it's sort of fun if you're into that. I mean, they get very, very beautiful and very intricate, very fast. Okay, cool. The main thing I just wanted you to see from that sample of field line diagrams is that the more complicated the charge source distribution, the more complicated the line picture is. More specifically, the more asymmetric the charge distribution, the more asymmetric the line diagram. I'll get into that. But please notice from just those pictures alone, I hope you see that field lines are arrows. They do have tips and tails, but they're not vectors. And the two big ways that you can tell that they're not vectors, they're doing something else. You read them and write them differently from vectors. The two main ways you can tell that they're not vectors is that, first of all, they don't have different lengths. If you might not have consciously noticed that looking at those pictures, but in no pictures did you really have like short or long. You didn't have any deliberately short or long arrows. All the arrows just kind of continued until they ran out of space on the page, if you think about it. And the arrows curved a lot of the time. They're not straight arrows and they don't have defined lengths. So they're very different from vectors. So now let me switch back to my board, hopefully, and I'll start explaining this. Okay, and I'm going to check the chat again. Okay. Better. Okay, thank you all for being so human. Okay, so here's some rules. And again, I can't emphasize enough. Like I gotta say, this is just like one of those millions of things. I'm gonna try to say this quickly. Like once I started being a physics major in college, once I got into E&M, the rest of my life had all these field line diagrams in it. Just like once you start doing physics, there's all these free body diagrams. At least in mechanics, there's like free body diagrams everywhere all the time. Or once you do any science, you just have graphs all the time. And I know everybody hates graphs in a way, to a point. I hated graphs until all of a sudden they clicked in and made sense to me. And then let me say, I was always like, why is everything always a freaking graph? Until I realized, because everything in science is a relationship, and graphs are actually the simplest way to capture a relationship. Like at a certain point, you just got to deal with graphs, right? If you're gonna, and you realize with graphs at a certain point, and many of you I think already have, with graphs at a certain point, you realize that even when you make a rough sketch of a graph is not a rough sketch, right? A graph is like a tool. Like a graph is a very precise model of reality. It's so precise that we end up analyzing and considering the graphs as our way of considering reality. Well, the same thing is true for field line diagrams. I have to say this again, because this is maybe new to a lot of you, but I'm going to talk about these field lines like for the next 3 days, for the rest of the course. And whenever I'm going to talk about these field lines, I'm going to talk about them as though they actually literally exist in space. Lines don't literally exist in space, but everything that is represented by these lines do exist in space. And these lines are the actual simplest way we can picture this information in our mind. So they are a strict tool. They're not approximate. They're like really, they're important to get your mind around. That's so it's not a sidebar and it's not like a detail. It's like the issue for the rest of your life, in at least in wherever fields are ever discussed. Field lines are the way of discussing them. So here are the rules, but there is something in the chat. I'm sorry, there's something in the chat. Oh, hello. Okay, sorry. Hello. Okay. Just making sure we're still okay. Okay. All right. So rule number 1. Okay, I'm going to look at the chat in a second. Sorry. I'll go back to that in 1 second. Let me just write this before I forget. I will turn the page back in 1 second, and I'll look in the chat. Hang on a second. Yes, I'm 1 second. Here. Wait. Oh, wait 1 second, please. Wait. Can you trade? How many like really good cards?
Yeah.
Like
8.
8. Like what's the best card of the 8 that you trade?
Blacephalon Rainbow.
So you're not trading Charizard or anything?
No, never, John. Oh, never.
So the Blacephalon is the best one?
Yes.
But and are you doing the usual thing of like there could still be, is anybody gonna, I don't want anybody to get upset. Could there be backsies?
Yes.
So it's how about it's a 1-day trial, and if everybody's comfortable with it after a day, then fine. Like
after today, and if everyone's
like you trade,
keep it.
Right, like give it a day for, you have a 1 day where everybody can do backsies, okay?
All right.
Okay, thank you for asking.
Thanks.
Okay, thank you. Okay, sorry. Okay, wait, I'm gonna look in the chat. Wait. Let me go back a page so you can read this. I'll read it out loud and I'll look in the chat. We're not trading a rainbow Charizard. That's all I'll say. Okay. So what I said, I'm just reading my handwriting. It says number 1A, and I'm going to explain this obviously, but it says number 1A, begin with a scaling factor. For example, for each 1 coulomb of source charge, we will draw 8 field lines. Okay, that's an example, but it's an example. Like it could be 10 field lines. It could be. You'll see why I picked 8 on purpose. If you look at my original drawings, that's exactly what I did. But what's not an example about it is when I say scaling factor, I mean how many lines will correspond. How many field lines will correspond to each coulomb of source charge. And even if you're talking about abstract diagrams like you just saw on the web where like the source charge is just called plus Q, like you don't literally have a number, then for Q, I drew 8 lines coming out of it, right, on the previous page I did. And then the idea would be then it says here, and I know there's stuff in the chat, then it says here, number 2B, for all subsequent diagrams within a given context, we stick consistently to the scaling factor and we distribute lines symmetrically. That says symmetrically. So, and I will look in the chat and all that, but like, so you notice what I'm trying to say so far is, if you looked at this field line picture right here, I just have the field line diagram from a positive point source plus Q. So what did I do? I decided, okay, my scaling factor is 8. So I drew 8 lines coming out of it, right? Why did I pick 8? I picked 8 lines. I drew them symmetrically, right? Because I'm trying to show the pattern of what the field would look like. And I picked 8 because it shows, 8 is just sufficient to show sort of radial emanation. It's like an asterisk or whatever. I could have picked 4. I could have picked 16. Picking 2 would have been a bad idea because it wouldn't really express the pattern. Right? You see my point? But I picked 8. And then the idea is that if I were trying to show something like the web was showing, like what's the field due to 2 point sources next to each other, and the other point source was like a double Q. Like if I had a plus Q over here and a 2Q over there, then out of the 2Q over there, 16 lines would emanate. That's the idea, you see. But no matter what, I'm always drawing the lines. When I start my diagram, I draw them as symmetrically as I can. Why? Because space is symmetric. The whole idea is there's nothing different about this region of empty space from that region of empty space. And there's nothing different about this direction in empty space versus that direction. So whatever a charge is doing to space, it's doing to all of space in the same way, right? So far what I'm saying is the first thing you do when you're creating a field line diagram, which you will be asked to on the final exam, or correspondingly, if you're trying to understand someone else's field line diagram, is you first realize that the number of lines coming out of a source is indicating how strong that source is. And it's doing it by virtue of some scale that has been predetermined, particularly if it's a computer drawing. Now, I'm going to pause. There's more rules to come, of course, but I do know there's something in the chat. Sorry, wait, what did people have? Two people have? Right, no, okay. So Evelyn, I know the question's been sitting there for 6 minutes, but like Evelyn's question is really good, but it's one of these funny questions where it's really, really good because in a way the answer is no. Like it was possible, yes, people do depict fields with vectors. And that's what we started off by doing. And you could type into Google Images like vector field diagram of blah, 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 blah. And in fact, and this is usually on the final 2, there are tools on the web which allow you to input information and then it will produce vector field diagrams for you. Vector field diagrams are useful and they are still used to today, yes. But the thing I want you all to see is that whatever is useful or proper or correct or informative about a vector field diagram, I'm here to argue that field line diagrams do everything that vector field diagrams do, but in a much smoother, simpler way. So the truth of the matter is that the field line diagram is like the tool that was advanced from vector field diagrams. I mean, most people today find field diagrams a more preferable way, not only to communicate, but to think in their minds. We tend today to talk about field lines as the reality of space rather than field vectors. But we always understand that lines are built from the vectors. So you can do a translation back and forth, but I don't know. But that's so that's right on point. I'm trying to show you a tool that gets us a lot more information in a more elegant way than vector fields. But if you understand vectors, this is all based on that. I'm going to ask Evelyn to like follow up when she can and just tell me if I've addressed what she just said, because it kind of is the whole point that I'm kind of here to say we would prefer field line diagrams over vector field diagrams from here on in, because they do everything vector field diagrams do, but they do it more efficiently. Okay, thank you. Yeah. Oh, okay, cool. Okay, well, now that you use the word nicer, I mean, now we're totally friends. Okay, cool. So great. Okay. I'm joking, but I'm not joking. Like, obviously, it's a taste issue in the end. If anybody in the class in the end still finds vectors more comfortable, I mean, it's like going in the metric system, like, or you know what I'm saying. This is ultimately the more efficient way, but do whatever's intuitive for you until the most advanced way is intuitive. Okay. But good question. Okay, great. And thank you for the follow-up. Okay, so that was rule number 1. The reason I'm stuttering around that question so much is I do want to reinforce again that if you do get stuck on what I'm talking about here, this is again one of those things in physics. I'm talking to all of you now about like step B in the alphabet. But if you get really lost, it could be very possible it's because you never got totally comfortable with step A. Like a lot of this is like forcing us all to find out how comfortable with vectors we are in the first place. So if at the end of the day, if all this field line stuff just ends up making some of you be like, this is too much. I realize I never really got vectors before, but now I'm just maybe kind of starting to understand vectors maybe from all this. Well, that's still an achievement and that is still progress. But yes, the goal here is to move. Okay, you get what I'm saying. Okay. So that's rule 2. Okay, now rule 3. Well, this is in A. Okay, I'm going to read that out loud. This is like a funny thing to say, maybe. I'm saying rule number 3A, or capital A, I guess. Rule 3A is every field line you draw, right? So you start with like dots on the page or sources on the page. You got like electron over here, or proton over there, or you've got a wire on the page, that you're depicting. So then you pick a scaling factor, then you start to draw these lines. Every line that you begin to draw, the tail of every arrow should be at a positive source, or it should come in from infinity. I will explain that more in a minute, but that's the rule. Lines start at positives, or they start infinitely far away, i.e. they start off the page. Similarly, and I will explain that more, but rule 3B, you might guess, every field line should end at a negative or go out to infinity. But one last way, with the rule 3A, I just went back to, and obviously tell me at any point if you want me to go back and forth. What I'm talking about in rule 3A are the tails of these arrows, because they still are arrows. They're not vectors, but they are arrows. So any tail that you see in a picture should either be literally at a positive source, like a proton, right? Or it should be, and I'll flash back to those Google images at some point, or any other tail you see should just be at the edge of the page. It should be like where the page got cut off, so the arrow got cut off. But the whole idea is you're supposed to infer, that arrow started way out there at infinite separation, and I just like don't have an infinitely large piece of paper or an infinitely large computer monitor. So every tail is either literally at a positive source, a proton, a plus Q, depicted in the picture, you probably usually somewhere near the center, or the tail, or any other tail of any arrow you see is like at the edge of the page, and it's just saying, oh, we just ran out of room. Similarly, every tip of every arrow you see is either landing on a negative. And again, if you want to, while you're listening, if you want to flip to Google Images and check for yourself, maybe that's a good idea. You'll see that any arrowhead, any tip that you ever see is either literally pointing directly, obviously, to some kind of negative source, of field activity, or the arrow is just like at the edge of the page, meaning this arrow is going on forever, but we ran out of room at the page. Okay, now that's really important, because the summary of this well, the summary of this rule or the implication of this, I'm going to say it one more time because this, again, I literally, I mean, I don't know what but you know, I've been out of college 30 years and I still vividly remember totally not understanding this when it was presented to me. And I mean, of course, it was presented a slightly different way, but like, I remember hearing this when they would say over and over again, every positive either, I mean, I could understand positives. I mean, I understood field lines start at positive and they end at negatives. That I could get. I didn't know why. I didn't really get it, but I got that that's what they were saying. But then they would say this other thing that I'm saying. They would say, or the positives, sorry, they would say, or the arrows come in from infinity, or they go out to infinity. And then when they threw that in, I was like, well, okay, but like, as opposed to what? Like, what are you saying? Like, I literally remember thinking, what are you saying? The arrow either starts at a positive or it starts like everywhere else. Like what, as opposed to what? Like, what are you telling me? Here's what they were, and I'm sure they were telling me, and I just didn't get it. What I'm saying here is that field lines never start nor stop spontaneously in blank space. They don't start or put this any way you want in your notes. A field line does not start or stop in the middle of space, or put another way, on the piece of paper or in the computer monitor. Whenever you're looking at field line diagrams, what you cannot find is any arrow that just starts like somewhere. The arrows, this is the deep sense in which they're not vectors. They don't have length. Put another way, all field lines have the same length. Or they don't have a meaningful length. I'll say this, no field line has a meaningful length. They don't start or stop in the middle of the page. If they start at all, they start on a positive. If they end at all, they end on a negative. Otherwise, they're understood to just be going on and on forever. They're rays. Field lines are rays, in effect, has a meaningful length, okay? That's super important. They're not, you cannot infer anything about magnitude from the length of a field line, because a field line, for all intents and purposes, doesn't have a length. I mean, if it happens to start on a positive over here and end in negative over here, then it has whatever length that is. But that doesn't mean anything. Okay, so that's rule 1 and 2 and 3. Yeah. Okay. Therefore, so well, yeah, okay. So rule 4. Okay. Okay. So now we're going to talk about what it is that we're showing with these diagrams. Direction. So field lines had better express direction and magnitude, just like vectors express direction and magnitude. I mean, we're still here to depict or represent or convey fields, and fields, force per charge, are vector quantities. They are still all the two crucial pieces of information to capture here still are direction and magnitude. But the question is, how are these lines doing that? Because they're not doing it the same way as arrows. So first, I mean, they aren't straight, these lines. So it's like a whole different ballgame here. So first of all, in terms of direction, I've used a lot of words to capture something that's sort of straightforward, actually. I'm saying what I wrote was direction of field at a point in space is represented by direction of tangent to the field line at a corresponding point in the diagram. Okay, that's a lot of words as usual. But what I'm saying is, if you looked at one of those pictures, or maybe right now on your side, if you look at any of those pictures on the web, those field line diagrams on Google Images, any point you pick in one of those pictures, any point you pick, if it's on one of the lines, like the line is curving in some kind of a way, imagine the line tangent to the curve at the point that you're looking at. And if you remember about tangent lines from derivatives and calculus and all that, the whole idea of a tangent line is to any given curve, there is one and only one tangent line, right? The tangent line to a curve at a point, the slope of the tangent line to a curve at a point captures the slope of the curve at that point, right? I mean, that's a very fancy way of saying if a curve is something that's changing its slope continuously, a curve gets steeper and steeper or less and less steep. If you want to know how steep a curve is at a point, you impose an imaginary tangent line at that point. You imagine in your mind a line that only intersects the curve at that point, that doesn't cross it anywhere else, right? And so the easiest example to picture is if you're looking at a curve that goes up and then down, and you picture the top of the curve, right, the local maximum, the line tangent to the curve at the top of a hump, right? The tangent line is horizontal. I hope you're with me on this, or maybe tell me if you're not, or if you are in the chat. But like if you picture like a parabola, like a y equals negative x squared type of function or something, at the vertex of that parabola, right? The tangent is horizontal. The tangent line has a slope of 0, meaning that when you get to the top of a curve, you're neither going up nor are you going down yet. Right then, at that moment, your slope is 0, right? So tangent lines are what we use to capture the steepness or the directionality of a curve at a point. So this is nothing new. At this point, if you sort of graph tangent lines and why we use them for derivatives and all that, it's the same idea here. If you want to know the direction of the field at a point in space, you look at a field line diagram, you look at the corresponding point in space that you're interested in the diagram, find the field line closest to that point, and whatever the line is doing at that point, I mean, you might not see the tip anywhere near where you're looking. The tip of the arrow might be like way over there, but wherever you're looking in a field line diagram, imagine a tangent line to it. The slope of the tangent line is the slope of the field line at that point. That's the direction of the field at that point. Again, by the way, if you're thinking, oh my God, he just said so many words just to say like the direction of the field line is the direction of the field. Yes, that's all I'm saying. The direction of the field line is the direction of the field at that point. But we have to actually think in terms of tangent lines because these field lines are now curving and changing continuously all the time. So really, it's the direction of the tangent line to the curve at that point shows the direction of the field. Okay, that's direction. And yes, again, really all I'm saying is the orientation of the line is the direction of the field. Kind of makes sense if you get what I'm saying. But now there's magnitude. Okay. Magnitude of field at a point in space is represented by okay, I'm going to pause for a second here. I'm going to tell you right now that I'm going to throw this to you guys for a minute just to make sure we're still all together. This is not, again, it's not to quiz you or anything like that, but we'll really know we're together. So I'm going to pause. So in a minute, I'm going to actually ask you for something in the direct chat. I'm going to say right now, if you're still following me, we're using these field line diagrams to represent the vector quantity known as field. So we're trying to understand how these field lines represent the two key pieces of information known as direction and magnitude. Now magnitude, is size. Somehow these field lines have to convey the size, the strength, the number of newtons per coulomb waiting to act at a point in space. What I am telling you is that they're not vector arrows anymore. These are vector quantities, but it's not a vector representation. So we can no longer say that the length of the line conveys the strength of the field, right? We could say that when we were just drawing vectors, and that was like Evelyn's question, right? If we drew a separate vector at every point in space, which again, we still could, it just gets really hairy really fast. If we drew a separate straight little arrow at every point in space, then indeed, the length of the arrow at that point on the page would represent the number of newtons per coulomb waiting to act at that point in actual space. And again, as long as we picked an actual scaling factor and stayed consistent with it, then it wouldn't just roughly depict it. It would like literally, precisely, computationally capture it. Okay, but that's not what's happening here. If you're still with me, we've now combined all of our arrows into these long, continuous flowing lines. And they're all of meaningless length, right? All of these lines are sort of in principle of infinite length or something. So we can no longer infer magnitude from line length, but we have to infer magnitude somehow. Otherwise, this whole program is a bust. Like magnitude of field must be readable from those pictures somehow. So I'm going to now pause and ask you in the direct chat, please, in the direct chat, I'm going to repeat, I'm going to say a question. I'm going to repeat it like 50 times. No, I'm going to repeat it a couple times. I'm going to ask all of you in the direct chat, either try to answer this question and it's direct. There will be no shame, either try to answer my question or somehow say something like, I understand the question is this, but I don't have an answer. Like either show me that you either hear the question, just so I know we're together, or give me an answer if you can. Or give me a wrong answer. And there's no shame in any of those, but or honestly say, okay, I've been spacing out. Like, can you repeat the question? And I will to a point. But here's the question. Here is the question. How is magnitude of field represented in a field line diagram? That's the question. I'll say it again in a minute, but I will say that if you just vaguely looked, remember, or now turn your attention to the field line pictures that I was just showing on Google, or frankly, I'll leave it. Oh, okay. And there's already one thing in the direct chat. That's great. I didn't even look at the content, but it totally looks like on point. I'm psyched. And to everybody, but I want to wait till there's a bunch of things in the direct chat before I respond. Okay, I'm seeing a lot of things. Awesome. And to all of you, that's great. And I will respond in a second. I don't know if I'll literally type out respond, but I will say to all of you, if you're trying to follow me at all, and this is not an easy, it's like everything else in physics. It's not easy, but it hopefully will make sense. Okay, I'm seeing a bunch of things in the chat. This is great. And I'm just going to say, even if you look at this picture right here, which is the simplest possible picture of all of just one point source, even in this picture, there is a way to read magnitude of field. So you're trying to ask, and there's so much in the chat now, I should shut up because it looks very clear that you guys are with me, and I really appreciate it. I'll just say that even in this picture, if you picked any random point in the picture that you're looking at right now, you could tell qualitatively at least like how strong the field was by some aspect of this picture. Okay, I'm not going to, there's so much, this is great. I'm not going to type out responses to everybody, but I'm going to just read quickly to myself, and I might read them out loud, but this is great. Hold on. But everybody, please try while I'm reading. Awesome. Oh, that's clever. I'm just trying to some of these. I'm not gonna respond to every one. I'm just reading things and okay. Oh, okay. I'm gonna repeat I love these answers. Almost a lot of these answers are dead on correct, by the way. Some of them are like close or reasonable, but they definitely do depict that you're understanding the question, which I appreciate. Some of them are very clear, but at least one person's asked me to repeat the question. I'm going to repeat the question one more time. The question is, and tell me if you're asking me to tell me if this makes it clear. The question is, what aspect of a field line diagram depicts or conveys or shows field strength? Like, how could you tell by looking at a picture? How could I tell by looking at this picture that the field strength over here at this point, P1, is like stronger, than the field strength over here, P2. In fact, that's what I'm saying to everybody. And by the way, I know hopefully if you're following all this, we all know that the field at P1 is stronger than the field at P2. Because we know how a point works. We know that the field gets weaker and weaker as we get farther and farther away from Q. So I know that you know that I know that you know that the field in this case would be stronger at P1 than it would be at P2. That is true. But my question here is, how is it that the diagram is getting that across? Because what I really want to know is, how could we tell a thing like that for a situation where we didn't already know the answer? Like those complicated things on Google Images. What aspect of the diagram is getting across field magnitude? That's the question. Okay. Cool. All right. Awesome. Okay. Again, if you put, I'm trying to save time. So today I almost want to name each one of you my name, who I promise you, I've read every single one in the direct chat. If you're in the direct chat, I'm happy, I'm psyched, and you should submit for points. And then if it turns out like whether you're right or wrong, you could submit for more points. Really, I'm not going to name you by names, and I'm not going to respond to each one right now. Oh, there's a lot in the chat. Okay, hold on. Wait, I skipped some. Hold on. Well, okay. Okay. Cool. Okay. There's so much in the chat. I'm so impressed. Okay. I responded to a couple of them for whatever reason, but I'm not. Oh. Okay. Okay, very quickly, I think. I'm not going to read names, but I am going to read some of these answers out loud, and I'm just going to read them fast, and I'm going to then say at the end which one. All right, here's some answers, okay? 1, maybe the density, like the arrows get closer together where the field is stronger and further apart where it's weaker. 2, maybe the thickness, boldness of the lines, meaning a thicker line is of a higher magnitude. I'm going to say right here, those 2 answers are different answers. Both those answers are different answers. Both of those are completely, they both do totally answer the question. Like both of those could actually work. To be clear, like, I don't want to get too, they're different. One of them is saying like how close the lines are together, and one is saying how thickly the lines are drawn. And either one of those could be a convention that we could adopt, honestly. And in some cases, we use both on computers, but one of them is more standard than the other, but they're definitely examples of answers that totally show understanding of the question. Then we have an answer by how close the test charge is to the source charge. Okay, so that's interesting. And it is true that the closer a test charge is to a source charge, the stronger the field would be. But we don't actually show the test charge in any of these diagrams. So that would be something that's true, but that wouldn't actually show us how the diagrams work, if that makes sense. But then we have the number of lines coming from the charge. Okay, I'll emphasize the part of that answer was like number of lines, maybe in a given region of space is on something. Other than the next person wrote number of lines, and then another person wrote coming out of the source. Again, true, Well, I'll keep reading. Okay, what was the question? I think I repeated the question at this point. And then someone said, I understand the question, but I'm not sure of the answer. And then the person wrote maybe the thickness or the thinness of the line, which again, okay, so I was kind of saying that is a very smart and reasonable answer. It doesn't turn out to be the standard convention, but like it could have been. Okay, could I repeat the question? I think I understand the question, but I'm unsure. Yeah, and someone wrote, due to the fact that electric field had both magnitude and direction, it could be represented by an arrow that has length, which is proportional to its magnitude, and that points in the correct direction. That's a very smart idea, but that's how vectors would work. Now we're into field lines, which are not vectors. Like we can't use, this is all, what do we do instead of length, if that makes sense? And then someone wrote, I guess the proximity of the arrows to each other. Okay, which is kind of like density of arrows or closeness of arrows or number of arrows per region or number of arrows. Someone else wrote maybe how closer the lines are drawn. All of these are very similar ideas, and they're good ideas. I'm not so sure about my answer, but I think maybe the closeness, the distance in between the lines, that's the other way of saying the exact same thing. Like if they're closer together, then I would imagine it's stronger field than when they are separated further. Okay, I hope you're hearing like an underlying theme throughout many of these answers. And someone said, okay, so someone definitely showed that they understood the question. Again, said the arrow shows the direction of the field exerts, and these are electrostatic fields. We're not up to magnetic fields yet, just to be clear. And then said the closer to Q, the stronger the strength. I just want to say again, a number of you are saying like the closer we get to the source, the stronger the field. That is true. But what we're trying to figure out, and so you can use that to try to figure out these preliminary diagrams. But what we're trying to answer right now is how do the diagrams work? What is the rule that the diagrams are following so that we can use these diagrams in situations where we don't already know the answer? Okay, I don't know if that, so right. So then when someone said, I mean, based on how close the points are to the source charge, the farther it is, the weaker it gets. Yes, that is true. But what I'm asking is, like, yes, the farther away we are from a source, the weaker the field is. That is a true fact. And it's an important fact. But what I'm asking here is, how is that being conveyed in these field line diagrams? And then I see, and I'm almost done reading these. Oh my God. Okay, sorry. First, I'll just read the last two things and then I'll tell you why I'm reacting with excitement. So first of all, another person just said, if the lines are close together, the field is strongest. Great. I mean, that's the thread I really want to, and all of these answers are great, and you're a great class. I'm not kidding. That's the thread I want to emphasize, the closeness of the lines. That's the theme I want to pick up on here in a minute. But then the reason I just shouted is that someone just said, we kind of tested this in lab today using a compass. And with this, I'll say closer. So first of all, that just got me excited because I haven't even asked you how that lab went today. I'm glad that you did that in the lab today. That's cool. And I'm glad that you picked up on that or took something away. That's great. That will help us tie this all together in the next 2 final days we have of class where, we still have to learn a lot and put it together for the final. So that's great that the compass thing like happened and stuck with you, but it also now explains to me why at least one person in the chat said magnetic field. Let me be clear for a second. Yes, I almost forgot. At the end of your lab today, you are actually making a segue into like the kind of final thing of this whole course, which is magnetic field. That is, I see now why in the end of the lab today, you got into magnetic field with those compasses. That's great. But what I'm still talking about right here in lecture right now, I'm strictly talking about electrostatic field. None of this is magnetic yet. I see why you're saying that because of lab, so that's great. But okay, so now to summarize what you guys are telling me, which is correct, I think someone just wrote it in the chat, but doesn't that mean that they're more lines? Yes, ultimately, someone just wrote in the chat, doesn't that mean that the more lines there are closer together, then that means the higher magnitude? Yeah. You guys said it a bunch of different ways, some more better than others, but ultimately, here's the point. Density is the key word here. So to get back to what we're trying to say, magnitude of, and I'm talking about E field, well, any kind of field really, but the only thing we're talking about right now is E fields. Magnitude of field at a point in space is represented by density of field lines in corresponding region of diagram, which is exactly, in other words, i.e. magnitude is represented by number of lines per area on the page. Magnitude in space is number of lines per area in the diagram. So, to use this, and this is what many of you were saying, especially when I was reading right at the beginning of the chat, we're looking for how do these lines show magnitude. Now, a couple of you said this really clever. I want to do a shout out. A couple of you said this clever thing of like, maybe the thicker you draw the line, the denser the field would be there. Like that would make sense. Like that could be a thing. We could do that. It would get very hard to do after a while though, because we'd have to have like this whole thickness scaling sort of range and a whole thickness palette. And for every possible dense, like it would be hard, but we could do that. I mean, that shows that you understand the question. And the truth of the matter is in some computer renderings and some different kind of computer programs, sometimes they'll use something like color, or brightness of the lines to show the strength of the field at that point. Like you could do that, but the actually much more easy standard thing to do is use the density of lines, the number of lines in a unit area on your page. I'm going to say this again. The number of lines, literally the number of lines per unit area on the page or on the computer monitor, the number of lines per unit area in a given region of the picture represents the strength of the field at whatever point in space is being represented by that region on the paper. That's why every time I use the word corresponding in these rules, when I say corresponding, I mean whatever part of the picture corresponds to whatever part of space we're trying to represent. So if you want to know how strong the field is at this point in space, you look at that corresponding area on the page and you look at how many lines are in the area, and assuming that everything has been drawn to scale, then the density of the lines, number of lines per unit area, that shows the field strength. So qualitatively, if you just look at this picture here, like the beautiful thing about this, like even though thickness is very clever, and again, I mean that, it's very clever. It shows you understand the question. Like if you were designing this, that could be a very cool design, or color or brightness could work. But the thing about density is that it happens automatically. If you just look at this picture right here, just automatically from this picture, as we get closer to the positive Q, the lines are bunched together. Right? There's like 8 lines per like 1 square centimeter. Then as you get farther away, the lines are automatically more spread out, right? And they're spread out in a pattern, like up here. Like I can tell from this diagram that the field here, the field there is stronger than the field there. But I can also tell that if I went like a corresponding distance away over here, the field would be the same at both of those P2s because the density of lines is the same. You see what? And again, I know that many of you said in the chat, like, okay, as you get stronger to this, as you get closer to the source, the field gets stronger. Yes, I know that. But the point is, how is it being conveyed in the diagram? It's being conveyed by density of lines. So as things get really complicated, when you look at those pictures on Google Images or whatever, any region on the page where the lines are really crowded, really dense, that means strong field. Wherever they're spread out, it means weak field. And it's all to scale as long as you've picked a scaling factor. It's all representative. Like, of course, we really believe there's an infinite number of these lines really in space. And of course, when I say lines, I don't mean that there's literally lines, but the information captured by the lines. But they're everywhere. But once we pick a scaling factor and draw everything symmetrically, then boom, we get this representation of direction and magnitude. So I'm going to keep going. Okay, so that was rule. Okay, Now things get, hello. Okay, so now rule 5. Okay, I'm going to explain this hopefully a bit more quickly than the last thing I explained, but there's something in the chat. Oh, yes, of course. Sorry. Okay. 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 Okay, great. Thank you. Okay. Okay. Just changing the. Okay. Oh, sorry. One second. Okay. So we're almost done with the rules, thankfully. But notice now with the rules we've set so far, so the idea is that you pick a scaling factor, and then you got like positive sources. You're depicting anything. You could be depicting the field lines of a helium atom. So it's like, oh, sorry. Yes. Can I move back to the yes? Yes. Oh, wait, the diet. Wait, hold on. Sorry. What is this? Something in chat. Yeah. Okay. I think I'm getting absolutely. I can go back, but I think I'm being asked to go back to 2 different places. So hang on. I think one person wants me to go back here. I think someone wants me to go here. Cool. But is this where you want me to? Oh, okay. But then I think also maybe. Oh, okay. Okay. But then I think someone else also wants me to go to the other page. Tell me if I'm going too fast. Okay. Well, tell me, the person who's asking for this page, just tell me when you're set with this page, and then I'm going to go to the. Okay. You're both. Oh, okay. All right. So that was that. Blah, blah, blah. Okay. So now what I'm saying is, so you're trying to draw one of these, and again, like I'm not saying you're going to have to draw. Oh, wait. Oh, wait. 3A on this. 3A. Oh, 3A. Yeah. 3. Oh, okay. Okay, great. Thank you. All right. What I'm saying right here, and again, I don't know. I found this very abstract when it first came my direction. I'm just trying to make it as unabstract as I can, but it's real. It's really important. It is abstract because it's like it's hard to picture. But that's the other thing. We're talking about fields, which we really believe are everywhere in space. And what we're trying to do with all these diagrams is help us picture it, because it's really hard to picture what we're talking about otherwise. And we are talking about something that exists in space and time, right? Like this is really where physics is physics. It's not just mathematical computations. So the physical depiction is really like the heart and soul of these ideas. So when I keep talking about how you would draw these things, I'm not trying to kid you into thinking you're going to be drawing a million of these for the rest of your life. Like you're going to have to draw like 1 or 2 on the final exam, probably. But even if you never have to, but even if you use computers or something, the real issue is by me telling you how they're drawn, I'm really trying to tell you how you understand them when you look at them. Okay, it's one and the same thing, right? It's like literacy of diagrams. So if you imagine, like if you're trying to draw the field line diagram of a helium nucleus or due to a helium nucleus, then you pick your scaling factor and you start drawing lines coming out of the positive charges, and then every line, and you pick a certain number and you draw them symmetrically, and then then every line that you've drawn, then you make it land. Every line that you can, you make it land on the negative, right? So if it's equal and opposite negatives, if it's equal and opposite charges, then every line that came out of the positive will end up landing on a negative, and you'll sort of be done. But if they're not equal and opposite, then some line, like if the positive is bigger, you'll have a whole bunch of lines coming out of the positive, and some of them will go to the negative in a symmetric way. But all the leftovers, if the positive was bigger than the negative, then the leftover positives that don't have a landing spot on the negative, they'll go off to infinity, if that makes any sense. But then you're always trying to draw as symmetrically and simply and smoothly as you can, because the whole idea is space is symmetric and smooth before things are put into it to interrupt its symmetry and smoothness. So the simplest, smoothest, most symmetric way that you can follow these rules as we proceeding to make a diagram allows then for the possibility that these lines start curving, right? I mean, as you saw in the initial diagram, if you have a positive, if you have like a plus Q over here, and you have a and you have a negative Q over here, right? If they're equal and opposite, like this would produce something like this on its own, right? And this would produce something like that on its own. But if they're close to each other, right, these would be what the vectors would be. But we're supposed to draw continuous lines sewing up all the vectors, right? So what it ends up looking like, the field line diagram in this, if you're drawing the simplest possible, smoothest possible way to follow all these rules as we have so far, you find that lines start curving, right? Like the all the arrows in between the two, sure, they're all going straight from positive to negative, so you get a line like that. But like the line from here to there, like curves, and the line from here to there curves. You see what I and they start curving more and more as you get farther and farther away from that. And again, if you can right now, go back to the Google images and see that lines can curve. They do curve frequently, but they don't cross ever. Why do they never cross? Because remember that each field line is a representation of the net electrostatic force per charge happening anywhere in space. In other words, these field lines are the result after we've added up all the vectors that were produced by, and this goes back to Evelyn's question from before, but it also goes back to all of the hard computation that we did last week just to add 2 vectors together at a point in space, right? All we did last week, and I think it was hard. I think it was a lot of math, but all we were doing last week was picking a point in space and adding the vector there from one dude to the vector from another. All of that was to add 2 vectors together. And what's the net result? A vector, right? So the point is, if we have a complicated source charge distribution, we have all these vectors everywhere in space that are all being added together and then creating new vectors. And then all the vectors are supposed to be sewn together into a line. So when we're all done at the end of the day with these field lines, we're trying to capture the net result, the superposition, the sum of all of these forces per charge waiting to happen due to all of these sources. So the line is what is drawn once all of the addition has been taken into account. So 2 field lines can never cross Because if they cross, that means you haven't finished making your diagram yet, if you know what I mean. Like that's an interim stage. The field line itself shows the result after we've crossed everything together. And that's another reason, okay, sort of back to the Evelyn thing, another reason that we love these field line diagrams is that at the end of the day, they take into account, they capture all of these mathematical details already having been done. At the end of the day, the smooth picture of these flowing lines is showing the net effect on space of everything that's in space. So I'm almost done with these rules, but I hope you understand. But you know, I hope you see what I'm saying. All of this, like all of physics, I don't know, to some of you, this seems simple enough that you probably think I'm overcomplicating it. And some of you probably think this seems very complicated. Anything is possible. But what I am assuring you, no matter how it feels to you right now, all of what I'm saying is as simple, not how I'm saying it, but what I'm saying is as simple as it could be and no simpler. This is the simplest possible method physicists have come up with for capturing and holding in their minds this very complicated idea that information from everything in the world is everywhere in space. That's what this is all about. The simplest possible way to model, picture, and compute from the information in space due to the things that are in space. Okay, so bottom line of rule 5, field lines totally can curve. They frequently do, but they cannot cross. If you're trying too hard to keep them straight, you're doing something wrong. And if you're allowing them to cross, you're doing something wrong. So that's number 5. Then number 6, like rule number 6. Okay, this rule, which doesn't have a part A and B, says in a diagram, as you look farther and farther, farther and farther we look, I guess I should say, we look. Like if you're looking at a diagram, any of those diagrams, the farther away your eyes travel from the source, the charge sources, the source charges, the farther away, in other words, the more your eyes start going to the edge of the page, the more the pattern of lines should look simpler, should look more uniform. In fact, strictly speaking, when I say uniform lines, what I really ultimately mean is parallel lines. The less complicated the line pattern should be. And the least complicated a line pattern could be, if you really think about it, would be parallel lines. Why do I say that? Because you all already told me that the density of lines indicates the strength of field, right? So what are parallel lines? Parallel lines are lines that are not getting any more dense or less dense. Like parallel lines means they're not getting closer to each other. They're not getting more bunched. They're not getting less bunched. So perfectly parallel lines would mean a perfectly uniform field strength. The farther away you look from the source configuration, no matter how, the more simple parallel, the more uniform the field should look. And if you think about that, that really ought to make sense, because many of you are telling me in the chat and other places that in space, So in space, if we have a really complicated like charge distribution somewhere in space, like we have like 3 helium atoms over here and like 17 beryllium atoms over there, or saying, all this complicated stuff. Field lines are doing all these complicated things nearby the charges. But as you get farther and farther away from the charges, like the fact that helium is, like, if helium is like 5 centimeters away from beryllium, then if you're like 2.5 centimeters from one of them, that makes a big distinction. Like you might be really close to the helium and really far away from the beryllium. So the lines are doing all kind of funny things. But as far as once you get like miles and miles away from both, you're basically equally far from both, right? So the field should, the distinctions in the field should grow less and less relevant as you get farther and farther away. If you get infinite, as you approach infinite separation from some source charge, you should approach a state of space that is more or less as though nothing was there. I can't say it any simpler than that, but the lines should start being more and more parallel as you get to the edge of the page, is what I'm saying. So finally, and this is the last rule, okay, so the bottom line, for whatever it's worth, is if you follow the first 6 rules, if you dive in to draw a diagram or to understand a diagram, and you have the first 6 rules in mind, which are almost somewhat follow from one another once you get the basic idea, then the final idea is, like, given the first 6 rules, we just draw lines as smoothly, as simply, as symmetrically as we possibly can, as long as we don't violate the first 6 rules. A field line picture is meant to be as smooth and as simple, as patterned, as symmetric, as self-similar as it can possibly be, as long as we're following all the first rules, i.e., to scale, positives create the lines, negatives accept the lines. Density of lines must depict magnitude. Tangents to lines must depict direction. The real truth of the matter is, as long as you strictly obey the first 3 rules and you obey the last one, then all the rules in the middle naturally work themselves out as it is. I mean, once you get the hang of this, it's basically just like draw the simplest arrangement of lines you can, given that you're only allowed to start at positives and you're only allowed to end at negatives, and you have to keep a consistent scaling factor. If you draw the simplest possible arrangement of lines that you can, given those, then what you get almost automatically is a proper field line diagram. What I'm really saying is, much like force free body diagrams, once you get it, they take care of themselves, and they end up revealing computational results that you couldn't get without drawing the picture. I thought forever that only people that understood how fields worked could draw these pictures. And therefore I unconsciously thought that. And forever I thought only people that understood how fields work could read these pictures. It turns out to be the reverse. If you really sort of practice a little bit and get down into the trenches with how these pictures work, then you end up understanding fields. Don't expect yourself to understand fields so that you can read the pictures. Try to get used to the pictures, and then you will understand fields. Honestly, that's how it works. The result of all this, and I know it's been a thick class, and I know we have 45 more minutes for good or for bad, and there is something else we have to do with all this. The takeaway of all this is field lines represent, okay, I'll be a better, hold on a second, a field line pattern. Okay. The takeaway of this, which we're going to use for the rest of our lives, i.e. 2 days, field line patterns represent distributions of raw information throughout space, right? Again, all this talk is like how information exists in space. Again, let me just keep reminding you, you put a proton right here in space, and what we believe is there are newtons per coulomb waiting to pull or push in some direction at every point in space. Like there's a given, if you put one proton here in a point in space, what we believe is that at every other point in space, automatically, there will be a certain number of newtons per coulomb waiting to push or pull in a certain direction at that point in space, like a specific number of newtons per coulomb waiting to push or pull in a very specific direction at every point in space due to the one proton that's here, right? We believe there's like such that if you put another proton somewhere else in space, it would get pushed with a certain number of newtons in a certain direction, right? That's what we believe. That newtons per coulomb are waiting everywhere in space the minute there's a proton or a electron, or for that matter, a kilogram, in which case it would be newtons per kilogram. So the minute you put something, sorry, okay. The minute you put something in space, a point of charge or a point of mass, we believe there's information everywhere in space. I shouldn't say the moment. I mean, there's a delay, but like automatically as a result of your putting a, sorry, interruptions. When we find a proton or an electron in space, then we find corresponding information everywhere spread out in space in a certain distribution, a certain pattern. We call that distribution or that pattern the field. We picture it as a bunch of lines. The pattern of the field lines represent distributions of this raw information throughout space. And the whole idea, if you know, after all of what I'm saying with all these rules and all that, if you take a step back and you just look, if ever in life someone says, here's the field line diagram for that situation, and you see this like complicated looking thing, you'll see something that's maybe complicated, but it'll be as complicated as the source which created it. And you will notice if it's a proper field line diagram, no matter how complicated it is, it will have some kind of patterns or symmetry involved in it. The whole idea is if there was nothing in space, space would be purely symmetric. There would be no lines in space. If you put one dot in space, you get a very simple pattern of field lines in space, just radial lines emanating forever. The more complicated the source that you put into space, the more complicated the field line diagram. What do I mean by complexity? What I really mean specifically is asymmetry. Field line diagrams are only as asymmetric as the distribution, the source distribution that created them. And that's not just an observation. That's not just like a sidebar. Like that's like the whole point is that the field line picture shows us what information there is in space. The field line picture tells us what space knows about something happening somewhere in space, and it knows it, so to speak, by virtue of the asymmetry of the field lines. The more asymmetric the field lines are, the more asymmetric the source distribution is. The field lines convey information in this sort of old traditional way of, as the famous quote goes, what information is in this context. Information is a difference that makes a difference. I mean, that's a cliche and that's like silly, but I'm saying space by itself would be full on sameness. The whole essence, I don't know exactly what space is any more than you do, but I know some key properties of space. I know that one cubic centimeter of space over here cannot be distinguished from 1 cubic centimeter of space over there. That's called the homogeneity of space. Space is the same from one equal-sized volume to another equal-sized volume. I also know that this direction in raw space cannot be distinguished from this direction in raw space. That's called the isotropy of space. What I'm saying is space is, I don't know exactly what space is, but I know whatever it is, it's the same everywhere. So if there was nothing in space, the field lines would be the same everywhere. The more complicated things we put in space, the more complicated the field line diagram gets. And the field line diagram is what tells space over here what is happening over there. That's what the field line diagram is all about ultimately. If you really understand how to read field line diagrams, then you're like space yourself. If you see a bunch of arrows over here all coming together and like all pointing here, then you know the field is very strong here. And if all the arrows are coming over there, you know there's something close by over there that's causing the field. The field line diagram over here tells space what is actually existing as particles of charge or mass or something over there. Okay, that's the takeaway. And all of this, I know we still have a half hour, and I know it's a lot. There's still something we have to do. But I'm going to take a breath for a second. I'm going to say, by the way, I keep like I yell because I get excited about all this. I keep saying that if you put a source charge, a point source of charge somewhere in space, then there's newtons per coulomb waiting everywhere in space, even before any other charge comes along to experience it. Why do I keep saying that? Like, where did I get all this in the first place? I got it because what we're talking about here in the first place are forces that are fundamental, that act at a distance. Remember, everything I'm saying can be applied to gravity. It can be applied to electricity. And as you saw in the lab today, thank you for bringing it up, it could also be applied to, ultimately, to magnetism. What do those three things have in common? Well, mathematically, they're all inverse R² forces. But physically, what they all have in common, unlike friction, unlike the normal force, unlike the tension force, what gravitation, electrostatics, and ultimately magnetism all have in common is they all seem to act through empty space without touching. The reason we believe in all of these fields is not because we want to. It's not because we want to make life any more complicated than it already seems to be. It's because life is complicated. It's because, because I've never said this clearly, I'm going to say it right now. If you have a proton over here, it pulls on what we know experimentally, what you saw in the lab is that, and what you see every day in your regular life is that some things seem to be able to affect other things without touching them, right? I'm glad someone brought up, you brought a compass closer to a wire and the needle started moving. It didn't touch the wire, I don't think. It just got near the wire and the needle moved. Somehow, some communications seem to be able to occur through empty space. We get so used to it because things fall to the ground all the time in our lives, and because we've been playing with magnets since we were kids, we get so used to it that partly, sometimes we forget truly how bizarre that is, that we only partly forget. We kind of get used to it because things fall to the ground all the time. But in a way, we never get used to it. And that's why magnets are always fun when you're a kid. There is something sort of mystifying and delightful when something can push or pull something else without touching it. That's why magnets are fun. I mean, honestly, like when they are fun. But I have to take a step further than that. I'm saying qualitatively, whenever action at a distance can occur, that means something very deep below the surface of macroscopic contact is happening. But let me go a step further. The minute you believe the math at all, the minute we have any evidence to suggest that F equals GMM over R squared, or F sub E equals KQQ over R squared, or whatever, the minute the math starts demonstrating itself to be consistently true, the minute we know that the force is in precise magnitude dependent on the inverse of the square of the distance between the two objects, like, and it doesn't even matter what the formula is, as long as we believe there is an equation, then that's a staggering realization. I'm going to say it right now for anybody who's still listening to me. It's a staggering realization to believe that the proton pulls the electron with a strength that depends on how far away the electron is. Or it's a staggering realization to believe that the sun pulls on the earth with a strength that depends on how far away the earth is. Because, I will say this for like 2 more minutes, then we'll get back to math that we need. But like, let me just make sure. Just raise your electronic hand if you're hearing me right now. Oh, okay. Well, that's one. Okay. So just you may want to write this down or something at some different points. Because we're saying all this abstract stuff about fields, and it is abstract, but I'm telling you to believe in them. And I'll tell you the reason we believe in them, the reason this is really part of science, it's not just an invention to make your life hard. The reason and thank you for raising your hands. I totally appreciate it. And I did catch that. The reason we believe that the information is sitting in space from one object, even before a second object comes along, is not because we want to. We don't want to. But if we didn't believe in them, we'd have to believe in something much, much worse and more complicated because if you believe in the math of the inverse R squared law, then bear with me for a minute. That means if you believe that the sun pulls on the earth with a strength that depends on how far away the earth is, think about it for a moment. That means that if the sun reaches out and grabs the earth through empty space by whatever mechanism anybody wants to believe in, then the earth gets closer to the sun, right? I mean, if all other things being equal, if the sun reaches out and gravitationally pulls on the earth and the earth gets closer, or if you don't like that, if you drop a brick to the ground, if the ground reaches up somehow through empty space and pulls down on a brick, so that the brick starts falling to the ground. If you believe this math, this descriptive math that seems to keep being supported by experiment after experiment, then that means that as the brick gets closer to the ground, or as the earth gets closer to the sun, then somehow the sun readjusts its force magnitude in response to the new distance, right? I mean, it means that as a brick falls to the earth somehow takes into account the new input, the new R, puts it into some equation somewhere, and then grabs on with a higher F. I'm not lying. I mean, that's what the math implies, that if the sun pulls on the earth and the earth gets a little closer, now the sun pulls on the earth more. Well, that means that somehow the sun over here must be getting the updated information about the Earth's new location. There's no way around it. Can I say that one last time? If we believe F equals GMM over R squared, or if we believe F equals KQQ over R squared for like protons and electrons, it means every time a proton pulls an electron through empty space, as though that wasn't already sort of hard to believe, it means that as the electron gets closer to the proton gets information updates. It knows physically knows the new location of the electron and then pulls with a correspondingly higher force. And every moment that the electron gets closer, the update somehow comes to the proton. I mean, how does that work? How does it take time? Does it happen instantaneously? This recognition is what drove Newton crazy at the end of his life. Like Newton himself had a really hard time with that. As everybody should when they first think about it. We are saying, if we believe these equations, we're saying that an object over here somehow knows the vital stats of an object over there, such that every time the object over here changes its vital stats, the object over here learns the update. So somehow this information of object number 2 is made available to object number 1 through empty space. So do I understand how God does that? Or no. Do I understand how the universe is so amazing that it pulls that off? No. But what we're saying is, apparently it happens. So our word for that idea that somehow the information of this object is available through all of space to any other object that comes along, that fact, which seems to happen all the time, that information updates of every object in space are available at every other point in space, every other object, that whole idea we call a field. We're not saying we're not, it's just like any other simple word. We're not saying that we really understand it. We're saying that's the word for this whole phenomenon that seems to be happening. Newton didn't like it either. He didn't have the word field. The word came after him. But if you don't have to believe in the field, but if you don't believe in the field, you have to believe in something even wackier. The field is the simplest possible model we could put in our mind for this phenomenon that appears to occur, which is somehow stuff in space seems to know where and how big everything else in space is, because somehow pulls and pushes occur between objects in space throughout empty space. The field is that idea. Okay, sorry. Again, what's my takeaway is that the field isn't an extra complexity in your life. It's an attempt to simply model something that seems to already be a complexity in life. Oh, cool. Yeah, thank you. No. Okay, I'm just gonna say someone's put something cool in the chat, like sort of like a crying emoji, and said that's excellent. On fact, if you found what I just said at all confusing or jarring, then you're with me. If you don't totally get what I just said, then you do get my law. I'm saying space does something very staggering. I'm not expecting you to grasp the whole thing right now, but I do want you to know that we didn't just invent the field notion just because like we're looking for trouble. The field notion is our simplest possible way to get our minds around something that is so unfathomable, but that it literally did drive Newton himself crazy. I mean, I don't have time for that whole discussion right now, but believe me, it's a very hard thought, and it took till Einstein to help us make any. But it just seems to be true. Otherwise, we wouldn't be able to predict orbits with such accuracy or put a person on the moon or whatever. Okay. Oh, sorry. Someone has their hand up. Is that a question or is it just from a hand up from before? Or Christina, sorry. Is that for a hand from before? Oh, and Dante, sorry. Are your hands up from before? Oh, okay. Or if you have a question, definitely ask it. But now okay. Okay. All right. Now I know this is a lot as usual. But again, remember the whole point of the course. The whole point of the course is unthingy things. We're here to learn about the motion through space and time of things that are not particles. So now what we're talking about is fields. They are part of science. They exist in space and time. We believe in them because of what we observe regarding actual particular matter in space and time. But fields are not matter. Okay. How can we start doing the math of fields? Now, all that was the picture of fields. There was a lot. But now with 20 minutes left, okay, I'm going to try to do this somewhat closely. I'm just going to get straight to equations now. Okay, I'm going to introduce in the last 20 minutes, and this is you're going to do a board meeting on this tomorrow, as I think you know. So I'm going to try to you'll really drill it home tomorrow in your board meeting. I'm going to try to give you the overview. In order to now start doing the math of continuous charge distributions, more realistic charge distributions, we're going to introduce a new notion now called flux, electrostatic flux. Okay. Approximately what flux means. All right, I'm just going to spit this all out. Okay, now I'm going to say this a bit quickly. Try to follow this. Oh wait, I'll write one more thing. And well, okay. Okay. Okay, I'm going to say this a little bit quickly. This is a whole new concept now. It's like sort of math and physics in a package, in a new package. You're going to practice and deal with it tomorrow in lab. The concept is flux, specifically electrostatic flux. Now, in English, what electrostatic flux means is amount of field strength flowing through or penetrating through or popping out of a given area. Okay, I'm going to flux is flux is amount of field strength coming through. Flux means flow technically, but flowing spatially through a given area. Let's do a little bit of let's talk about what a little bit of flux is, even before you do an integral or anything like that. If you have a little bit of area, an infinitesimal bit of area, a little two-dimensional region of space, like a little tile, a little square, imagine a vector sticking perpendicularly out of that area. Okay, like an area is not a vector, it's a two-dimensional region of space, right? But imagine that there's this little arrow, a little flag attached to the area that sticks out of it perpendicularly. Okay, so the direction of the arrow is necessarily perpendicular to the area. And imagine that the size of the arrow represents the size of that area. So the bigger the area, the bigger the arrow. But right now we're in an infinitesimal case, so they're infinitesimal. But so there's a little vector that represents an area. And the whole idea is that we use a vector to represent an area because now if the vector can show the orientation of the area, because like if you started rotating the area by 45 degrees or something, the arrow would correspondingly rotate 45 degrees. So the arrow is always pointing perpendicular to the area, but we always know that. So we can always tell by looking at this arrow, tip and tail, we can tell how the area is facing. And by the size of the arrow, we can tell the size of the area. So imagine that you go to any area you like and you ask, what's the electric field strength popping through that area? In other words, you ask, remember, if you want to know the field strength in some region of a diagram, of a field line diagram, the number of field lines per unit area in that region is what's showing us the strength of the field, right? So if you look at some area on a diagram and you count the number of field lines per area in that region, and then you multiply by the area that you just counted the lines, well, first of all, then what you would be doing is measuring flux. Flux is field strength times area. Let me back up for a second and make that more clear, or try to make that more clear. What flux is by definition in English is field strength times area. Flux is not a dividing, it's a multiplying. So it's like if you had a certain area and a number of field lines going through that area, you'd have you multiply the number of field lines per area times the area, you get the flux. It'd be some number. It'd be like newtons per coulomb times square meters, right? If you increased the density of the lines, like if you increased the strength, that would increase the flux. Or if you kept the same strength of lines, the same number of lines, but you looked at a bigger area, that would also increase the flux. Like flux is a multiplication of two things, field strength and size of area. And don't worry about why for a minute. I'm about to tell you why, but I'm just saying this is a definition right now. The idea of flux is amount of strength times area. Bigger the area, the bigger the flux. The bigger the strength, the bigger the flux. And if either one is zero, then the whole thing is zero. Okay? Now, if you're calculating flux, you take field strength, E, and you multiply it by ds. But those are both vectors now, like in that integral thing, right? They're both vectors. So there's a technique there. What we're technically doing is a dot product between those vectors. We're getting the scalar product between two vectors, just like we did with force times displacement equals work, right? Back in the day. This is just like that. Technically speaking, we multiply field strength, the field strength and direction vector times the direction of the area vector, but it's technically a dot product. So just like with work, we're only looking at the extent to which these two vectors are aligned with each other. And if you remember this little weird technicality that the area vector is designed to be like a little flag that's sticking out perpendicular to the area. So I know this is a lot, but what I'm saying then is if to calculate flux, I'm going to add a page, sorry. I'm going to add one page right here. Okay, we're talking about this new concept. It's a new concept. I'm introducing it right now called flux. Technically, like flux in Latin or whatever means flow. We don't mean flowing through time. We mean flowing through space. What do we mean by flowing? We really mean through. We mean perpendicular. What we're really saying here is if you want to know the flux, if you have a little area and you have a bunch of field lines going through the area, what we're going to do is multiply the strength of that field by the size of that area. But it's technically, it is a dot product. It's taking into account directionality of both vectors. And it's designed so that at the end of the day, you might have to think about this. At the end of the day, we're only multiplying components of field vectors or field lines that are in fact perpendicular to the area. Technically, what we're doing is multiplying field lines that are parallel to the arrow, the area vector that is already perpendicular to the area. So there's like a beat there you might have to think about. But at the end of the day, when we count flux, when we assess flux, when we measure flux, we are measuring how much field strength, how many field lines are busting through an area perpendicular to it. Short story long, I'm saying if there were a bunch of field lines that were going parallel to an area, that would not be flux at all. There could be a whole bunch of field lines, but if they're all parallel to some huge area, no matter how big the area is, no matter how many lines, if they're strictly parallel, they ain't no flux at all. If there are a bunch of field lines going at some angle to an area, then what we would do is take the component of each field line that is perpendicular to that area, we would count that, and we would multiply. So at the end of the day, when we're measuring a bit of flux, we're multiplying amount of field that is perpendicular to the area. But like why? And what am I talking about? And why is there an integral and all that? I'm just about getting to that. I'll get to the why first. Well, I'll get to the integral now. The reason that, strictly speaking, flux is an integral is the same reason that, strictly speaking, work from the beginning of the semester is an integral. Because if you just had a little bit of flux, if you had a little bit of area with a few field lines going through it, and it was such a small area that the number of field lines wasn't changing from one edge of the area to the other, then we wouldn't need an area at all. I mean, we wouldn't need an integral at all. We could technically say, in other words, technically, you could say if you want a little bit of area, I'm sorry, a little bit of flux would, strictly speaking, be field strength times a little bit of S stands for area because it's like surface. S stands for surface. So if you had a little surface that was little enough that the field lines over at one edge were the same number in the same direction as the field lines on another edge, then you would just multiply the field strength times the area, and that would be your flux answer. End of story. But if you have a big area, so big that the field strength has sort of space to vary continuously as you go from one edge to the other, then the only way to calculate the total flux, which I still haven't told you why I care, but this is a definition for the moment. If you wanted to know the total amount of field flowing through a total area, if things are large enough that field strength can vary continuously, then we do a continuous sum. We stand on one little bit of area, one infinitesimal bit of area, ask the number of field lines going through it perpendicularly, multiply the two together, throw that in our bag, and then step to the next little bit of area. Perform the same multiplication again, take that answer, throw it into our bag, step to the next bit of area. And we walk throughout the whole area, continuously adding up all these results, and the big net result at the end is an integral, a continuous sum, right? As we've discussed before. And so technically it's a double integral because we're technically adding up bunches of two-dimensional regions. Don't be intimidated by this. You may never have seen a double integral before. It's fine. You could think of it, if you like, as us walking along one direction. You could think of it as just a regular integral, just walking along a line, adding up the area, adding up the field strength, multiplying, adding up the field strength, multiplying, and then walking down the other dimension. It could be like an integral multiplied by another integral if you like. But in the end of the day, it's a two-dimensional integral. It's not as intimidating as it looks, but that's what flux is. Flux is the total sum of electrostatic field strength flowing through some area. That's what it is. Now we have 5 minutes left. Yeah, we have 5 minutes left. Just enough. That's what it is. You're going to do calculations with it tomorrow in the lab. But the first question, but it may sound very out of left field right now or sound very intimidating. One question that might help you tomorrow, you might ask, like, why? Like, why is this like suddenly coming into my life? Like, why do I care about field times area? And why do I suddenly now have to deal with dot products and integrals again? Well, there was a reason we did them at the beginning of the course. This is the reason. But the reason that they come into our life now is we spent all this time constructing this field line idea, for the last 2 hours. And we said that field strength is represented by number of lines per unit area on the page. I mean, that's what you guys told me correctly. Field line density indicates magnitude of field. So, as complicated as flux may sound, flux, it actually becomes the simplest, most visual, most tangible way to think, or one of the most ways to think about field, because if you're looking at a field line diagram, okay, as it says here, flux means field strength times area. But field strength, like literally, like magnitude of field vector, like newtons per coulomb, field strength is depicted by number of lines per unit area. So what flux, to read flux off a picture, off a field line diagram, to read flux is to read, or is to look at, or to measure number of field lines per area times area. So the areas cancel. This is on purpose. This is the point of flux. So what flux really is, this complicated mathematical integral that we are going to have to use in lab tomorrow and everything, this complicated integral called flux, what it really is the mathematics of looking at a field line picture and counting the number of lines. If you say that somewhere in a field line picture, there's a lot of lines, there's like 5 lines, and then over here, you say there's 10 lines, what you're saying is the flux over here is twice as much as the flux over there. Flux is the word for number of lines in a diagram. The more the lines, the more the flux, because again, number of lines per area is field strength. Field strength times area is what we call flux. So in a diagram, flux is number of lines per area times area. It's just number of lines. Okay. I'm going to tell you, we have 2 minutes left. I'm going to jump into your goal tomorrow in the not joke of a board meeting. And definitely it's like important and everything. Your goal is you're going to draw, like you're going to try to calculate the flux from like a point in a sphere and things like this. And it'll all look very intimidating until you get used to it. But remember, to count flux, you're counting up field lines, and you're only counting field lines that are perpendicular to a certain area. So you're going to be asked a bunch of questions in your board meeting tomorrow. But the ultimate conclusion that you're trying to drive towards, I'll tell you right now, that you're trying to get to is you're going to see, if you do things carefully tomorrow, you're going to see that if you draw certain closed surfaces, and you compute the flux through a closed surface, like I have 1 minute left. Wait, sorry, hold on. Like tonight, as soon as it's downloaded tonight, I promise. You're going to find if you have like a point source right here, and it creates a bunch of field lines, you're going to be asked tomorrow, like, what's the flux through the surface area of some sphere surrounding that point? Okay, it's going to look hard at first, but what you're going to find eventually, if you really think it through, is that the flux, the number of lines that goes through a surface surrounding some point source, the number of lines that go through that surface, if you follow this and think it carefully through tomorrow, you'll find that the flux won't depend on how big that surface is. It won't matter if it's a sphere of size radius 1 centimeter or a sphere of radius 5 centimeters, because the bigger the sphere, the more spread out the lines will be, but the bigger the area will be. And if you're really paying attention tomorrow, and if you're hearing me right now, you're going to find that the bigger and bigger spheres you draw, you'll get bigger and bigger areas, but you'll get field strengths that are weaker and weaker. And you'll find it's by the same amount. And if you're following me now and you pay attention tomorrow night, what you're trying to get at is if you draw a closed surface around some point source, you're going to find that the powerful thing about flux is the total result you get for flux won't change depending on the size of the sphere. It will only change depending on the amount of charge enclosed. This ENC means enclosed. It will only depend on the amount of charge enclosed by that closed surface, by that sphere. Now, obviously, I said that fast, but that's like the answer. That's like my one. I'm just giving you the answer tomorrow to sort of give you some motivation to hang in there. But it'll seem a little abstract, but the whole point of flux in the end is count the lines that hit a surface perpendicularly. Okay, I'm done. I know there's things in the chat. I'm not going anywhere, but you all can go. You've been very, very patient. You'll still get your exams, blah, 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 but I'll answer whatever's in the chat for here. I'll turn off the recording and then I'll answer any questions for anybody who hangs out. But thank you. All right, thank you. But if you put something in the chat, I will answer it now. Just bear with me for a second. Yes, bye. Bye. Hold on. Okay. I'll leave it. Bear with me for a second. Sorry. Let me just finish this. I'm not going anywhere, I promise. Hold on. Okay, I'm just finishing these notes for you. I'm going to post all this right now. I'm going to look in the chat. I promise I'll turn off the recording. I'm turning off the recording. Bye and thank you. But thank you guys for turning off.